Tonight, place your hand on the ground. Feel the earth beneath your palm. Solid, ancient, seemingly eternal. This planet has been here far longer than you can truly comprehend. And we modern humans with cities and technology and written history have been here for an eye blink. Less than an eye blink. A fraction of a second in a day that's lasted since morning until midnight. Now imagine this. What if we're not the first? What if another civilization rose before us, built cities, developed technology, and then vanished? Not thousands of years ago, not tens of thousands, millions of years ago, tens of millions, back when the continents were arranged differently, when the climate was alien, when life itself took forms we'd barely recognize. Would we know? Could we know? Or would time have erased every trace, grinding their cities to dust, burying their monuments under miles of rock, consuming every shred of evidence that they ever existed at all? I'm the Sleepless Astronaut, and tonight we're exploring a question that sounds like science fiction, but is actually serious scientific inquiry. It's called the Silurian Hypothesis, and it asks something simple yet profound. If an industrial civilization existed on Earth millions of years before humans, what traces would remain? And the answer should unsettle you. After enough time, almost nothing survives. Cities crumble, mountains erode, continents shift. The planet recycles its own surface, grinding it down, melting it, transforming it, destroying its own history. Give Earth enough time, and it erases nearly everything. So how would we know if someone came before us? What clues could possibly survive? And most disturbingly, have we already found traces without realizing what they are? Let's find out. Imagine compressing Earth's entire history into a single day. The planet forms at midnight. Life appears surprisingly early, maybe 4 in the morning. For most of the day, that life is simple, microscopic, invisible. Complex life doesn't emerge until evening. Dinosaurs rule for a while, then vanish, and humans? We don't appear until the final second before midnight. Modern civilization, everything you know, every city and monument and achievement happens in the last fraction of that final second. We are extraordinarily recent, which means we're sampling an absurdly small slice of this planet's story. We're seeing the final frame of a movie that's been playing for hours and assuming we know the entire plot. But here's what should humble us. The Earth has been capable of supporting complex life for a very long time. Not just complex life, but intelligent life, maybe even technological life. The conditions were right. The planet was stable. There was time, vast stretches of it, when something could have emerged, risen, fallen, and been completely forgotten. And time is the problem, because time doesn't just pass. It destroys. Wind grinds mountains to sand. Rain dissolves stone. Rivers carve through rock. Glaciers bulldoze everything in their path. And beneath the surface, the planet is constantly recycling itself, swallowing old crust and creating new, erasing its own past, like a chalkboard being wiped clean over and over. Now picture a civilization existing not thousands of years ago, but millions. Deep time. Time so vast that continents have moved, that entire mountain ranges have risen and eroded away, that the shape of the world itself has changed. How much would survive? What evidence could possibly remain? The uncomfortable answer, almost nothing. Not because that civilization was weak or primitive, but because geological processes are relentless. Given enough time, Earth consumes nearly every trace. Let's imagine humanity vanishes tomorrow. Instantly, completely gone. Our cities stand empty. Our infrastructure abandoned. What happens next? For a while, things look familiar. Buildings stand. Roads remain. Objects persist, but decay begins immediately. Wood rots, metal rusts. Concrete cracks as water seeps in, freezes, expands. Plants reclaim everything, roots breaking through pavement, vines pulling down walls, forests swallowing suburbs. Within decades, cities start looking less like cities and more like ruins. Within centuries, they're archaeological sites. Within thousands of years, they're mounds of earth with strange materials buried inside. Now skip ahead. Not thousands of years, but millions. Jump forward through time until continents have shifted, until mountains have risen where valleys once were, until the entire landscape is unrecognizable. What's left of us? Almost nothing on the surface. Erosion has been thorough. Wind, water, ice all working constantly to break down, grind away, erase. Cities are gone. Monuments are dust. Even massive structures are scattered fragments mixed with sediment, buried under layers of rock, transformed by pressure and heat into something that barely resembles what they once were. The only things that might survive are chemical, traces in rock, anomalies in sediment, strange concentrations of elements that shouldn't cluster naturally. Synthetic molecules that don't occur in nature, though even these are breaking down, degrading, becoming harder to distinguish from natural compounds as time passes. And here's the critical point. We know what to look for when searching for traces of human civilization because we built it. We know our materials, our chemicals, our signatures. But if another civilization developed differently, used different materials, left different fingerprints, would we even recognize their traces? Or would we see something strange in geological data and explain it away as some unknown natural process? This is where things get uncomfortable, because there are anomalies, strange things in the geological record that don't quite fit our models, unexplained extinction events, chemical signatures that seem wrong, isotope ratios that puzzle geologists. Most of these have conventional explanations: volcanic eruptions, asteroid impacts, natural climate cycles, but some remain mysterious. And the Silurian hypothesis asks, what if some of them aren't natural at all? In 2018, two scientists, Gavin Schmidt and Adam Frank, published a paper asking a question nobody had seriously considered. How would we detect an ancient industrial civilization in the geological record? Not because they believed such a civilization existed, but because the question reveals something important about what evidence survives and what doesn't. They called it the Silurian hypothesis, named after a science fiction show where intelligent reptiles evolved before humans. The name is tongue-in-cheek, but the science is serious. If a civilization rose and fell millions of years ago, what traces would remain for future geologists to find? The answer is sobering. Very little survives intact, but certain signatures might persist. Unusual concentrations of elements, synthetic molecules that degrade slowly, isotope ratios indicating industrial processes, rapid changes in atmospheric chemistry, extinction events coinciding with climate disruption. Not cities or artifacts or fossils of their builders, but chemical fingerprints, subtle anomalies in rock, things easily missed or misinterpreted. And here's what makes this genuinely unsettling. Earth's geological record contains exactly these kinds of anomalies. Events where something dramatic happened, climate shifted rapidly. Oceans acidified, species died en masse, and we don't fully understand why. We have theories, but the evidence is ambiguous, the data incomplete. Take the Paleocene-Eocene thermal maximum. About 55 million years ago, global temperatures spiked rapidly. Carbon flooded into the atmosphere and oceans. Life was disrupted worldwide. The conventional explanation involves massive volcanic activity or methane releases from ocean sediments. But the carbon isotope ratios are strange. The timeline is compressed. Some details don't quite fit. Or go further back. The Permian extinction, the worst in Earth's history when most life died. We think massive volcanic eruptions caused it, releasing carbon and sulfur that poisoned the atmosphere and oceans. But the scale seems wrong somehow. The extinction happened faster than volcanic activity alone seems to explain. There are gaps in our understanding. These are almost certainly natural events. Volcanism, asteroid impacts, climate feedbacks. Earth doesn't need intelligent intervention to create catastrophes. But the Silurian hypothesis forces us to ask, how would we know the difference? If an industrial civilization collapsed catastrophically, triggering runaway climate change and mass extinction, what would distinguish that event from a natural disaster in the geological record millions of years later? The answer is disturbing. We might not be able to tell. The signatures could be identical. Rapid carbon release, ocean acidification, temperature spikes, mass extinction. These things happen naturally, but they also describe exactly what an industrial civilization collapsing would look like from millions of years' distance. So how would we actually search for evidence of ancient civilization? What would we look for? First, anomalous materials, elements or compounds concentrated in ways that don't occur naturally. Plastics take millions of years to fully degrade, and even then they leave chemical traces. Rare earth elements used in electronics concentrate in ways natural geology doesn't produce. Synthetic molecules that require industrial processes to create might persist in trace amounts even after vast time periods. The problem: these signatures degrade. They spread through rock. They mix with natural compounds. After enough time, they become nearly indistinguishable from background chemistry. You'd need to know exactly what to look for and where to look, and even then you might find nothing simply because geological processes erased it. Second, isotope ratios. Different industrial processes leave different isotopic fingerprints. Burning fossil fuels shifts carbon isotope ratios in a specific way. Nuclear technology creates isotopes that don't occur naturally or occur in proportions nature never produces. These signals can persist longer than chemical traces encoded in rock, potentially detectable millions of years later. But again, the challenge is distinguishing artificial from natural. Natural processes also create isotope anomalies. Volcanic eruptions, meteorite impacts, biological processes all shift ratios. You'd need multiple lines of evidence converging to make a compelling case. Third, rapid changes. Industrial civilization doesn't develop slowly. It explodes going from pre-industrial to advanced technology in barely 2 centuries for us. This rapid transition should leave a distinctive signature. Sudden appearance of new chemicals, rapid shifts in atmospheric composition, accelerated climate change, all happening in a geological instant. Natural events can also be rapid by geological standards. but the specific combination, particular chemicals appearing suddenly, specific isotope changes, climate disruption of a particular type, might be distinctive enough to recognize if you knew what to look for. Fourth, extinction events. Industrial civilization stresses ecosystems. Habitat destruction, pollution, climate change, these drive extinctions. If a previous civilization rose, industrialized, and then collapsed catastrophically, it might create an extinction event with a particular profile. Not asteroid strike sudden, not volcano gradual, but something in between, with chemical signatures suggesting industrial activity preceded the die-off. The difficulty: extinction events happen naturally. Earth has experienced 5 major mass extinctions and numerous smaller ones, all from natural causes. Distinguishing an artificially triggered extinction from a natural one after millions of years might be impossible. So we're left with this. Detecting ancient civilization requires finding multiple subtle signals that align in ways suggesting intelligence rather than natural process. It requires examining rocks for chemical and isotopic anomalies, looking for rapid changes in atmospheric composition, studying extinction events for unusual patterns. And even finding all of this wouldn't prove ancient civilization. It would only make it a possibility worth considering seriously. And here's the most unsettling part. We're already limited in where we can look. The Earth's crust isn't some uniform layer we can sample freely. We have access to maybe 1% of it, the thin surface layer, exposed rock faces, drill cores from mining and research. The rest is buried too deep, or it's underwater, or it's been subducted into the mantle and melted away entirely. Plate tectonics is particularly devastating for preserving ancient evidence. The ocean floor, which covers most of the planet, is constantly being created at mid-ocean ridges and destroyed at subduction zones. The oldest oceanic crust is barely 200 million years old. Anything older has been recycled, consumed, erased. If a civilization existed on an island chain or coastal region more than 200 million years ago, the very ground they built on no longer exists. It's been pulled beneath a continent and melted back into the mantle. Even continental crust, which is older and more stable, isn't immune. Erosion removes material constantly. Sediment buries things under layers that eventually become rock. Heat and pressure from being buried transforms that rock, altering its chemistry, destroying delicate signatures. Mountain building crumples and deforms everything. What seems solid and permanent is actually in constant flux, just operating on timescales too slow for humans to perceive directly. So we're not just looking for a needle in a haystack. We're looking for a needle that might have rusted away in a haystack that's been scattered by wind, buried under new haystacks, partially burned and relocated to an entirely different field. The odds are not in our favor. And yet, despite these obstacles, despite the relentless destruction of geological processes, despite our limited access to Earth's deep history, we keep finding strange things, anomalies, events that don't quite fit. Moments in the geological record where something dramatic happened, and we're not entirely sure what or why. Most of these are natural. Earth is violent volcanic eruptions, asteroid impacts, climate shifts, can all create dramatic signatures in rock. But every so often, researchers find something that nags, something that almost fits the natural explanation, but not quite. Something that requires invoking multiple rare events happening simultaneously to explain. something that would make more sense if we were willing to consider possibilities we normally dismiss out of hand. The Silurian hypothesis doesn't claim we found evidence of ancient civilization. It claims something more subtle and more disturbing. We might not be able to recognize such evidence if we found it. Our assumptions about what to look for, about what's possible, about Earth's history, these assumptions might blind us to signals that are already present in the data we've collected. Imagine being a geologist examining sediment from millions of years ago. You find anomalous chemical signatures, unusual isotope ratios, evidence of rapid climate change, species dying en masse. What's your first assumption? Volcanism, probably. Maybe an asteroid, some combination of natural disasters. You don't think ancient civilization, because that's not on the list of possibilities your scientific training prepared you to consider. But what if it should be on that list? Not as the most likely explanation, not even as a probable explanation, but as a possibility that shouldn't be dismissed automatically. What if some of the anomalies we've found and explained away with increasingly complex natural mechanisms are actually simple if we're willing to consider that intelligence arose before, industrialized, and left traces we're seeing but not recognizing? This is the uncomfortable space the Silurian hypothesis occupies. It's not claiming ancient aliens visited Earth. It's not claiming Atlantis was real. It's asking something more fundamental and harder to dismiss. Are we sure we're the first technological civilization Earth has produced? And if we're not, how would we know? The answer to that second question, how would we know, is what makes this genuinely unsettling, because we might not. The evidence might be there, subtle and strange, buried in geological data we've already collected but interpreted through frameworks that don't include the possibility we're trying to detect. We might have already found the fingerprints of ancient civilization and explained them as volcanic eruptions, as climate cycles, as asteroid impacts, as anything except what they actually are. Or maybe we haven't. Maybe all the anomalies are natural. Maybe we really are the first time intelligence and technology emerged on this planet. Maybe the assumption we've always made that we're first is correct. But we can't know for certain. And that uncertainty, that gap in our knowledge, that possibility we might be wrong about something so fundamental, that's what makes this question worth exploring. Not because ancient civilization probably existed, but because we can't prove it didn't. And the fact that we can't prove it didn't reveals something important about the limits of our knowledge, about how much of Earth's deep history remains inaccessible, about how thoroughly time erases evidence. So tonight, as you look at the ground beneath your feet, consider this. Beneath the surface, beneath the soil and rock and sediment, lies 4.5 billion years of history. Most of it is lost, destroyed by geological processes we can barely slow, let alone stop. What remains is fragmentary, ambiguous, open to interpretation. We're reading a book with most of its pages torn out, written in a language we only partially understand, describing events so far in the past that even the fundamental geography of the planet has changed, and we're trying to reconstruct the plot, fill in the gaps, understand what happened during the vast stretches of time when we have no direct evidence at all. Maybe we're the first chapter where intelligence appears, or maybe we're a later chapter, repeating a story that's been told before, building on ground that once held cities we'll never find, asking questions that were answered and forgotten millions of years before the first human existed. We don't know. We might never know. But the possibility alone should change how we see ourselves, our place in time, our relationship to this ancient planet that birthed us and might have birthed others before us. Let's explore what we do know, what we found, and what it might mean if we're willing to consider possibilities that seem impossible. Open a geology textbook and you'll see Earth's history laid out in neat layers. Periods with names like Cambrian, Devonian, Jurassic, each one representing millions of years, each one supposedly understood, cataloged, explained. Life emerged here, diversified there, died in this extinction event, recovered in that radiation. The story seems complete, settled, finished. But look closer and cracks appear. Large sections of the geological record are simply missing gaps where rock should exist but doesn't, where entire time periods vanished through erosion or were never deposited in the first place. We call these unconformities, and they're everywhere. Millions of years of history just gone, as if someone tore pages from a book. Even where rock exists, preservation is selective. Fossils form rarely, requiring specific conditions, rapid burial, anoxic environments, mineralization before decay. Most organisms that ever lived left no trace. Most species that existed are completely unknown to us. We're sampling a tiny fraction of life's diversity, the lucky few that happened to die in circumstances allowing preservation. And that's just for fossils' actual biological remains. For evidence of behavior, of technology, of civilization, preservation becomes exponentially less likely. A shell can fossilize, a bone can mineralize, but a tool, a structure, these decay, corrode, crumble, disappear long before geological processes can preserve them. Think about what archaeologists find from ancient human civilizations. Stone structures, pottery shards, metal objects buried in favorable conditions. Even from just thousands of years ago, most of what these civilizations created is gone. Fabric rotted, wood decomposed, paper vanished. We're left with fragments, the most durable pieces. Everything else erased by time. Now scale that up. Not thousands of years, but millions. The preservation problem doesn't just worsen, it transforms. You're not looking for objects anymore. Objects won't survive. You're looking for chemical signatures, isotopic anomalies, geological traces so subtle they're easily dismissed as measurement error or natural variation. And even these traces degrade. Organic molecules break down. Synthetic compounds decompose. Isotope ratios mix with surrounding rock, diluting, spreading, becoming harder to distinguish from background. After enough time, even chemical fingerprints fade to near invisibility. So what are we actually looking at when we examine ancient rock? We're seeing a heavily edited version of reality. The geological record isn't a faithful chronicle of Earth's history. It's a fragmentary document full of gaps, biased toward certain types of preservation, destroyed and rewritten by geological processes operating over immense timescales. Most of Earth's surface rock is sedimentary layers of mud, sand, silt that accumulated in oceans, rivers, deltas. These layers can preserve fossils, chemical traces, evidence of atmospheric composition. But even sedimentary rock gets metamorphosed, transformed by heat and pressure into new forms where original signatures are altered or destroyed. Bury rock deep enough, heat it enough, and it recrystallizes, erasing the details it once preserved. and large portions of Earth's crust aren't sedimentary at all. Igneous rock from volcanic activity or mantle upwelling, metamorphic rock transformed beyond recognition. These rocks contain almost no information about surface conditions when they formed. Whatever existed on the surface above them is simply gone. Then there's the coverage problem. Geologists have sampled rock from around the world, but coverage is patchy. We've examined outcrops, drill cores, exposed formations, but vast regions remain unstudied ocean floors, except for shallow samples, deep continental interiors, areas beneath ice sheets or dense jungle. We've literally seen only the tip of the iceberg. And crucially, we've primarily studied recent rock formations from the last few 100 million years. The deeper you go, the less attention has been paid, partly because older rock is rarer and partly because it's been so transformed that extracting information becomes increasingly difficult. This creates a profound problem. If evidence of ancient civilization exists, it's probably in exactly the places we haven't looked carefully. Older rock, heavily metamorphosed formations, regions that were destroyed by plate tectonics, areas we can't access. We're searching for subtle anomalies in the small fraction of Earth's crust we can actually examine in rock young enough to potentially preserve traces, informations that haven't been too heavily altered. It's like trying to solve a murder mystery when most of the crime scene has been demolished. The evidence has decomposed. You only have access to one room of a 100-room building, and the events happened so long ago that even basic facts about what the building looked like are uncertain. But here's what makes this genuinely intriguing. Despite these enormous obstacles, we keep finding things that don't quite fit. Events in the geological record that are hard to explain, anomalies that require invoking improbable coincidences, chemical signatures that seem wrong somehow that make geologists uncomfortable, even as they propose conventional explanations. Take carbon isotope ratios. Life preferentially uses lighter carbon isotopes, so biological activity creates distinctive signatures in rock. When you find sudden shifts in these ratios, it indicates something changed: dramatically massive die-offs, vegetation changes, ocean circulation disruption. These shifts appear throughout the geological record, and usually we explain them with volcanism, climate change, ocean chemistry alterations. But sometimes the magnitude or timing seems off. The shift happens faster than expected. The isotope values hit extremes that are difficult to reproduce through known natural processes. Multiple anomalies cluster together in ways that each individually can be explained, but collectively strain credibility. None of this prove ancient civilization. Each anomaly has proposed natural explanations, but it does illustrate how we interpret data through frameworks that don't include technological civilizations as possibilities. When we see strange isotope ratios, we think volcanism. When we see rapid climate change, we think orbital variations or tectonic events. We don't think civilization because that's outside our framework. And maybe that's correct. Maybe all the anomalies are natural. But the Silurian hypothesis suggests we should at least consider the alternative, not as the most likely explanation, but as something that shouldn't be automatically dismissed. Because if an ancient civilization did exist and did leave traces, those traces would look like anomalies in the geological record. They would look strange. They would be hard to explain. They would be exactly the kind of things we're already finding and explaining away. The geological record is incomplete, biased, fragmentary, and heavily edited by time. It's not a reliable chronicle of everything that happened. It's a damaged document with most pages missing, and we're trying to reconstruct the story from fragments. Maybe that story only includes natural processes, or maybe it includes chapters we're not recognizing because we're not looking for them. Life on Earth has nearly ended multiple times. Not gradually, not through slow decline, but catastrophically. Periods where the diversity of life collapsed, where most species vanished, where the planet transformed into something alien and hostile. We call these mass extinctions, and they're written clearly in the fossil record layers where abundant life gives way to barren rock, where diversity plummets, where the world fundamentally changed. 5 major mass extinctions have occurred, plus numerous smaller ones. Each has explanations: asteroid impacts, massive volcanic eruptions, climate shifts, ocean anoxia. Natural disasters on scales difficult to comprehend, turning Earth into a place where most life couldn't survive. These weren't quick either. Many lasted thousands or even millions of years, extended catastrophes during which ecosystems collapsed and struggled to recover. The most famous is the dinosaur extinction. An asteroid struck the Yucatan Peninsula, triggering global firestorms, blocking sunlight with debris, causing rapid cooling followed by longer-term warming. 75% of species died. The world that emerged was fundamentally different from what existed before. Mammals, previously small and marginal, diversified into the forms we recognize today. Without that extinction, we wouldn't exist. But the dinosaur extinction wasn't the worst. That distinction belongs to the Permian extinction, sometimes called the Great Dying. This occurred around 250 million years ago, and it nearly ended complex life entirely. 96% of marine species died. 70% of terrestrial vertebrates vanished. The oceans became acidic and anoxic. The atmosphere turned toxic. For millions of years, Earth resembled a dying world, barely clinging to habitability. What caused it? The conventional explanation involves the Siberian traps, massive volcanic eruptions that released enormous amounts of carbon dioxide and sulfur dioxide over millions of years. This triggered runaway greenhouse warming, ocean acidification, oxygen depletion. Feedback loops amplified the disaster. Warming oceans released methane from seafloor deposits, causing even more warming. Life spiraled toward extinction as habitats vanished and the planet's chemistry became hostile. That's the story we tell, and it's probably correct. Volcanism on that scale, sustained for that long, would absolutely cause catastrophic disruption. The evidence fits: flood basalts in Siberia dating to the extinction, geochemical signatures indicating massive carbon release, climate proxies showing rapid warming. Everything points to natural disaster, but look closer and complications emerge. The timeline is compressed. The extinction happened faster than massive volcanism alone seems to explain. Some groups of organisms died off before the main extinction pulse. Others survived in pockets that shouldn't have been habitable, according to our climate models. The carbon isotope excursion, the shift indicating massive carbon release, is more extreme than volcanic sources alone easily explain. None of this disproves the volcanic hypothesis. Complex systems don't always behave predictably. Feedback loops can accelerate events. Maybe our models underestimate volcanic output. Maybe there were multiple causes converging. Maybe we're missing some key mechanism that would make everything fit together neatly. Or maybe, and this is where the Silurian hypothesis becomes unsettling, we're looking at evidence of civilization collapse without recognizing it. Think about what industrial civilization does to Earth. We release carbon from fossil fuels, causing atmospheric CO2 to rise rapidly. Oceans acidify as they absorb that carbon. Temperatures increase, triggering feedback loops. Melting permafrost releases methane. Dying forests release more carbon. Changing ocean circulation disrupts climate further. If we continued unchecked for thousands of years, industrializing more intensely, burning through available resources, the damage would be enormous. Now imagine civilization collapses, resource depletion, climate disaster, social breakdown, whatever causes it. The immediate harm stops, but the damage persists. The carbon we released remains in the atmosphere for thousands of years. Ocean acidification continues. Climate continues warming as slow feedbacks unfold. And this warming might trigger natural processes that amplify it. Methane releases from seafloors, carbon release from dying ecosystems, changes in Earth's reflectivity as ice melts and vegetation changes. The civilization is gone, but the catastrophe it triggered continues, possibly for millions of years if feedbacks are strong enough. And what would this look like in the geological record millions of years later? Rapid carbon isotope excursion, ocean acidification, global warming, mass extinction. Exactly the signature we attribute to natural volcanism because that's the only mechanism our framework includes. The Permian extinction might be entirely natural, probably is natural. The Siberian traps provide a clear mechanism. But could we tell the difference between massive volcanism and the long-term consequences of industrial collapse? If a previous civilization existed, industrialized over thousands of years, depleted resources, triggered runaway climate change, and then collapsed, what distinguishing features would that leave versus a massive volcanic event? The answer is uncomfortable. We might not be able to tell. Both involve rapid carbon release. Both cause ocean acidification. Both trigger warming and extinction. The isotope signatures might differ slightly. Fossil fuels have different isotope ratios than volcanic carbon, but after millions of years, after mixing and contamination and geological transformation, those differences might be undetectable. And it's not just the Permian. Other mass extinctions show similar features. The end Triassic extinction, rapid carbon release, warming, acidification, extinction. The late Devonian, prolonged environmental stress, ocean anoxia, species collapse. The Ordovician, rapid glaciation followed by equally rapid warming, causing massive die-offs. For each we have natural explanations. Volcanism, asteroid impacts, orbital variations causing climate shifts. And these explanations are probably correct. Earth is violent enough to cause mass extinctions through purely natural means. It's done so repeatedly. But the question lingers, how would we know if one of these wasn't natural? If even one mass extinction was triggered by technological civilization collapsing catastrophically, what signature would distinguish it from natural disaster after geological processes have had millions of years to obscure the details? We might not have any way to know, and that's the truly unsettling part. Not that ancient civilization definitely existed, but that if it did exist and did trigger catastrophic environmental collapse, we might be looking directly at the evidence without recognizing it. interpreting it as volcanism, as asteroids, as natural climate variation, because those are the only possibilities our scientific framework considers. Mass extinctions reveal Earth's capacity for violence, but they might also hide evidence of intelligence's capacity for self-destruction, and we have no reliable way to distinguish between the two after enough time has passed and enough geological processing has occurred. The evidence looks the same, the mechanisms converge, and we're left with ambiguity we can't resolve. Everything leaves traces. Every process, every activity, every event alters chemistry in some way. Burn wood and you release carbon with specific isotope ratios. Smelt metal and you scatter rare earth elements in distinctive patterns. Run nuclear reactions and you create isotopes that don't exist naturally or exist in proportions nature never produces. These chemical fingerprints are how we track processes across time. Geologists examine rock chemistry to understand ancient volcanism, asteroid impacts, ocean conditions, atmospheric composition. Each process leaves distinctive signatures, elements, isotopes, molecules that persist in the geological record, sometimes for millions of years, encoding information about what happened when that rock formed. Industrial civilization creates distinctive chemistry. We synthesize molecules that don't occur naturally: plastics, pesticides, countless organic compounds created for specific purposes. We concentrate rare earth elements through mining and processing. We alter isotope ratios through fossil fuel combustion. We create entirely new isotopes through nuclear technology. Our chemical fingerprint is unmistakable, but that's now in recent rock and materials we can study directly. What happens after millions of years? How long do these signatures persist? And more critically, would we recognize them if we found them in ancient rock? Start with synthetic molecules, plastics, for instance. We've produced billions of tons, spreading fragments across every environment. Some plastics degrade quickly, but others persist for thousands of years. Eventually, all plastics break down, but they don't vanish completely. They fragment into smaller pieces, eventually reaching molecular scale. And those molecules, while degraded, retain distinctive chemical structures indicating synthetic origin. In theory, traces of plastics could persist for millions of years, especially in anaerobic environments, deep sediments, sealed deposits, anywhere oxygen can't reach to facilitate decomposition. The molecules would be degraded, fragmented, mixed with natural organic compounds, but potentially still detectable with sufficiently careful analysis. Except we've never looked for them. Geologists examining ancient rock aren't searching for degraded synthetic molecules because there's no reason to expect them. If they appeared in data, they'd likely be dismissed as contamination, measurement error, or unusual natural compounds. We don't have frameworks for interpreting them as signs of ancient technology because that's not on our list of possibilities. Rare earth elements present similar issues. These elements, scandium, yttrium, lanthanides, occur naturally, but in low concentrations and specific geological patterns. Mining and industrial processing concentrate them artificially, creating anomalous distributions. An ancient civilization using these elements for technology would leave traces unusual concentrations, elements occurring together that don't naturally co-occur, distributions that don't match any known geological process. Would we find them? Maybe, Rare earth deposits are actually surveyed regularly since these elements are valuable for modern technology. If there were large anomalous concentrations, we might have noticed. But small anomalies, degraded deposits, traces in unusual locations, these could easily be missed or misinterpreted as unknown mineralization processes. Then there are isotopes. This is where things get genuinely interesting because isotope ratios can persist almost indefinitely. Rock billions of years old still preserves isotope information from when it formed, and certain industrial processes create distinctive isotope signatures that shouldn't occur naturally. Nuclear technology is the clearest example. Fission creates isotopes with specific ratios indicating artificial origin. Some of these isotopes have long half-lives, millions of years, meaning they'd still be detectable long after the civilization that created them vanished. Plutonium-244 has a half-life of 80 million years. Curium-247, 15 million years. These don't occur naturally in significant quantities, so finding them in ancient rock would be extraordinary. But how thoroughly have we looked? Nuclear isotopes are primarily studied in recent sediments contamination from weapons testing, reactor accidents, waste disposal. Deep-time geology doesn't routinely screen for them because there's no reason to expect them in rocks millions of years old. If anomalous isotopes exist in ancient formations, we might not know because we haven't looked. Fossil fuel combustion also leaves isotope signatures. Organic carbon from fossil fuels has distinctive carbon isotope ratios lighter than most natural carbon sources because biological processes preferentially incorporate lighter isotopes. Massive fossil fuel burning shifts atmospheric and oceanic carbon isotopes in a measurable way. This signature appears clearly in recent sediments. The Industrial Revolution is visible as a carbon isotope excursion in lake and ocean cores. But similar excursions appear throughout the geological record, usually attributed to volcanism releasing deep carbon or massive die-offs of organisms altering the carbon cycle. Could any of these ancient excursions be from industrial activity? How would we know? The isotope shift from fossil fuel burning overlaps with shifts from volcanism. You'd need additional evidence: synthetic molecules, rare earth anomalies, extinction patterns to distinguish industrial from natural origins. And as we've established, that additional evidence might not survive or might be unrecognized. There's also the problem of dilution and mixing. Chemical signatures don't remain isolated. Groundwater moves through rock, carrying dissolved compounds. Diffusion spreads molecules from high concentration to low. Geological processes mix layers. After millions of years, a concentrated chemical deposit becomes dispersed, its signal weakened, its origin obscured. Imagine a civilization that existed for thousands of years. They produced millions of tons of synthetic materials, concentrated countless rare earth elements, released distinctive isotopes. When they vanished, those materials remained, buried in landfills, scattered across landscapes, concentrated in waste repositories. Now fast forward 10 million years. Erosion has redistributed everything. Sediment has buried it under new layers. Groundwater has leached and spread soluble compounds. Tectonic activity has deformed, heated, transformed the rock. What remains? Traces, faint anomalies, chemical signatures so diluted and mixed with natural background that distinguishing them from normal geological variation becomes nearly impossible. We could be swimming in evidence of ancient civilization-degraded synthetic molecules, scattered rare earth concentrations, faint isotope anomalies, and not recognize it because it's too faint, too degraded, too mixed with natural chemistry to stand out clearly. Our analytical techniques are sensitive, but they're designed to find clear signals, not subtle anomalies that might or might not mean something, and there's confirmation bias. If you find an unusual chemical signature, your first assumption is measurement error. Check the instruments, rerun the analysis. If the anomaly persists, you look for natural explanations, unknown mineralization, unusual weathering, contamination from recent sources. You don't think ancient civilization, because that's not in your training, not in textbooks, not something peer reviewers would accept without overwhelming evidence. So chemical signatures that could indicate ancient technology might be present in the geological record, degraded but detectable, waiting in rock formations we've already studied, or in places we haven't looked carefully. But we wouldn't recognize them. We'd explain them away, fit them into natural frameworks, dismiss them as not particularly interesting. This is the insidious part of the Silurian hypothesis. It's not claiming we've definitely found evidence. It's claiming we wouldn't necessarily recognize evidence if we found it. Our frameworks, our assumptions, our trained interpretations, all of these guide us toward natural explanations and away from possibilities we don't expect. And maybe that's correct. Maybe every chemical anomaly really is natural. Maybe the isotope excursions are just volcanism. Maybe unusual element concentrations are just weird mineralization. Maybe we're not missing anything, but we can't be certain. And that uncertainty, the possibility that evidence exists, but we're not recognizing it, that's what makes this genuinely unsettling. We're confident in our interpretations, confident in our understanding of Earth's history, confident that we'd recognize something as dramatic as ancient technological civilization. But would we? After millions of years of degradation, dilution, transformation, and mixing, would the chemical fingerprints of ancient technology be clear enough to recognize? Or would they be subtle anomalies we've already found and explained away, never realizing they might be traces of something extraordinary? Picture a mountain, massive, solid, seemingly eternal, the kind of geological feature that defines landscapes, that appears unchanging across human lifetimes, that looks like it's been there forever and will remain forever. Now compress time. Watch that mountain across millions of years. It's not stable. It's not permanent. Weather attacks it constantly, rain dissolving minerals, ice expanding in cracks, wind abrading surfaces. Rivers carve through it, carrying away dissolved rock grain by grain. Glaciers bulldoze entire valleys. The mountain shrinks, erodes, gradually disappears. Given enough time, mountains become plains. Coastlines migrate hundreds of miles inland or seaward. Entire landscapes transform beyond recognition. And this happens not through catastrophe, but through ordinary processes, operating relentlessly across timescales we can barely comprehend. This is what time does. It destroys. Not quickly, not dramatically, but thoroughly. And if time can erase mountains, what chance does a city have? What hope for artifacts, for structures, for any trace of civilization? Consider what happens to a building abandoned in a temperate climate. Within years, the roof leaks. Water infiltrates, promoting rot and rust. Windows break, allowing birds and rodents inside. Plants take root in cracks, their roots expanding, fracturing walls. Within decades, the structure is collapsing. Within centuries, it's a mound of rubble, being slowly reclaimed by soil and vegetation. This is recent destruction, happening under conditions we can observe. Now scale it up. Not decades, but millennia. Not millennia, but millions of years. Not just one building, but entire cities, entire civilizations worth of structures, all being subjected to the same relentless processes. Metal corrodes, returning to oxide forms chemically similar to the ores it was smelted from. Concrete cracks and crumbles as water infiltrates, freeze-thaw cycles pulverize it, and chemical weathering breaks down the compounds, binding it together. Glass, surprisingly durable, eventually devitrifies or shatters into fragments that are further ground down by natural processes. Stone erodes, its surface worn away, its bulk gradually reduced. Nothing resists indefinitely. Everything, given sufficient time, returns to simpler chemical states, gets buried, gets transformed, gets scattered and mixed until its artificial origin becomes undetectable. And we're not just talking about surface processes. Burial itself destroys evidence. Sediment accumulates, rivers deposit silt, oceans lay down layers of mud, wind-blown dust settles. This burial can preserve things temporarily, protecting them from surface erosion. But burial also means pressure, means heat if buried deep enough, means chemical transformation. Organic materials, wood, fabric, paper, even plastics break down through biological and chemical processes, leaving at most faint chemical traces. Metals oxidize or are redistributed through groundwater movement. Complex structures are crushed, deformed, scattered. After burial under miles of sediment, after being subjected to heat and pressure and chemical alteration for millions of years, almost nothing remains recognizable. Plate tectonics makes things worse. The Earth's crust isn't static. It moves, driven by convection in the mantle below. Plates spread apart at mid-ocean ridges, collide at subduction zones, slide past each other at transform faults. This movement is slow by human standards, but relentless over geological time. Subduction is particularly devastating for preservation. When oceanic crust meets continental crust, the denser oceanic plate gets forced beneath, descending into the mantle where it melts. Everything on that plate, sediments, structures, any evidence of what existed there gets consumed, melted, recycled. The oceanic crust currently exists nowhere older than about 200 million years. Anything before that has been completely subducted and destroyed. This means if a civilization existed on oceanic crust or coastal regions that were later subducted, the ground they built on no longer exists. It's gone, melted back into the planet's interior, erased as thoroughly as if it never existed at all. Continental crust is more stable, less prone to subduction, but it's not immune to destruction. Mountain building, when plates collide and crust, crumples upward, deforms everything, heating and metamorphosing rock, destroying delicate chemical and isotopic signatures. Erosion continuously removes surface material, carrying it away to be deposited elsewhere. And even continental crust gets partially subducted or altered by tectonic processes over long enough timescales. Then there's metamorphism. Bury rock deep enough, heated enough, and it transforms. Sedimentary rock becomes metamorphic rock, sandstone becomes quartzite, limestone becomes marble, shale becomes slate or schist. During this transformation, the rock's internal structure changes. Minerals recrystallize. Organic traces are destroyed. Fossils are obliterated. Any delicate chemical signatures indicating unusual origin are erased. Even without extreme metamorphism, simple diagenesis, the chemical and physical changes that occur when sediment turns into sedimentary rock alters evidence. Pore fluids move through the rock, carrying dissolved materials, depositing new minerals, altering chemistry. Pressure compacts the sediment, breaking and deforming any structures embedded within. The resulting rock bears only simplified traces of what was originally deposited. Now layer all these processes together. A civilization exists, builds structures, produces materials, leaves traces. They vanish. Immediately, erosion begins working on what they left behind. Sediment buries some of it. Groundwater starts altering chemistry. Thousands of years pass, then millions. The continents drift. Climate changes repeatedly. Ice ages come and go. Glaciers scouring some regions and depositing sediment in others. Mountain ranges rise and erode away. Rivers carve new valleys. The traces of civilization, already degraded, get buried deeper, heated, deformed, chemically altered. Some end up in subduction zones and are destroyed completely. Others remain in continental crust, but become so transformed that their artificial origin is undetectable. A few, in very rare circumstances, rapid burial in anoxic sediments, isolation from groundwater, protection from heat and pressure, might preserve some recognizable features. But these would be extraordinary exceptions, rare enough that finding them would require incredible luck. And we're competing against natural processes that create similar features. Nature concentrates elements in unusual ways through hydrothermal activity, magmatic processes, weathering, and deposition. Nature creates complex molecules. Organic chemistry happens constantly in sediments. Nature even creates structures, concretions, septarian nodules, stromatolites, that can look artificial to casual examination. Distinguishing artificial from natural becomes harder as evidence degrades. A fresh artifact is obviously artificial, but a degraded trace after millions of years of alteration might be ambiguous enough that natural explanations seem more plausible than artificial ones, especially when artificial origin isn't expected. Time doesn't just destroy evidence. It creates ambiguity, makes certainty impossible, ensures that even if traces survive, they're questionable, debatable, insufficient to compel conviction. And this is without considering that we simply don't have access to most of Earth's crust to examine anyway. The ocean floors are inaccessible except for shallow sampling. Deep continental interiors are unexplored. Regions beneath ice sheets, beneath dense jungle, beneath urban development all remain largely unsampled. We're examining a tiny fraction of Earth's surface, and even that examination is focused on relatively recent rock formations that are easiest to access and study. If evidence of ancient civilization exists, it's probably not in the places we've looked carefully. It's probably in exactly the places that are hardest to access, in rock that's been most heavily processed by geological activity, in formations we have the least data about. And even if we found it, even if we examined the right rock and detected anomalous signatures, we might not recognize it as evidence of intelligence. Because time hasn't just destroyed the evidence. Time has destroyed our ability to interpret what remains. After enough geological processing, after enough transformation and degradation and mixing, the distinction between unusual natural process and trace of ancient technology becomes so blurred that making definitive claims becomes impossible. This is time's ultimate victory, not just erasing evidence, but making even the fragments that survive uninterpretable, ambiguous, insufficient. We're left with possibilities rather than certainties, with questions that might not have answerable solutions, with mysteries that time has made fundamentally unsolvable. If you wanted to find evidence of ancient civilization, where would you search? What rocks would you examine? What regions would you prioritize? The answer reveals just how limited our options actually are. Start with age. You need rock old enough that civilization could have existed before it formed, but young enough that evidence might still survive. Too recent, say, the last few million years, and we'd probably have noticed obvious artifacts. Too old, billions of years, and geological processing has been so extreme that almost nothing could survive. The sweet spot is probably somewhere between 10 million and several hundred million years ago, old enough that evidence would be deeply buried and heavily degraded, explaining why we haven't found obvious artifacts. Young enough that complete destruction isn't guaranteed, that some traces might persist in favorable conditions. But rock from this age range isn't uniformly accessible. Much of it is buried under younger sediments. Some has been metamorphosed beyond useful analysis. Some is on oceanic crust that no longer exists, having been subducted. What remains available is a small subset, biased toward continental shield regions and sedimentary basins that haven't undergone extreme deformation. Next, consider environment. Where would traces most likely preserve? Not on exposed surfaces erosion destroys too thoroughly. Not in high-energy environments like mountain ranges or active volcanic regions, too much deformation and heating. The best candidates are stable sedimentary basins, places where continuous deposition buried and protected materials quickly after civilization ended. Ancient lake beds are ideal. Lakes accumulate sediment continuously, burying whatever falls into them or washes in from surrounding areas. Anoxic conditions at lake bottoms can preserve organic materials and prevent oxidation of metals. Rapid burial protects from further weathering. Some lakes persist for millions of years, creating thick sedimentary sequences that might preserve extended time periods. Deep ocean basins are another possibility, though access is problematic. Continuous sediment deposition, anoxic conditions in some regions, protection from erosion, all favor preservation. But oceanic crust older than 200 million years doesn't exist anymore, limiting how far back you can search. And sampling deep ocean sediments is expensive and technically challenging. River deltas and coastal sediments might preserve traces from civilizations that existed near waterways. Rivers transport materials from wide areas, concentrating them in deltaic deposits. Rapid burial in these environments can preserve things that would decay on exposed surfaces. But deltas are also dynamic environments, constantly being reworked by flooding and channel migration, potentially destroying or scattering evidence. Coal deposits are intriguing candidates. Coal forms from accumulated plant material in swampy environments. If a civilization existed, their materials might have washed into these swamps and been incorporated into coal seams as they formed. Anthracite and bituminous coal has been extensively mined and examined, creating opportunities to notice anomalies. But most examination focuses on coal quality and chemistry for industrial use, not on searching for traces of technology. Caves offer another possibility. Protected from surface erosion, stable in temperature and humidity, sometimes isolated from groundwater flow, caves can preserve materials for extended periods. But caves accessible to hypothetical ancient civilization would mostly be near surfaces, meaning they'd be exposed to eventual erosion as landscapes evolve. Deep caves, protected from erosion, probably weren't accessible to surface-dwelling civilization. Then there are anthropogenic deposits, if they exist, places where ancient civilization disposed of waste, concentrated materials, built lasting structures. These would be the highest density sources of evidence, but they're also the hardest to locate without already knowing where to look. And after millions of years, even these deposits would be degraded, buried, transformed, scattered. So you're searching for needles in haystacks, except you're not sure which haystacks might contain needles. Most haystacks have been partially burned or scattered by wind, and you don't have access to most haystacks anyway. The search space is enormous, and the targets are ambiguous. But there are strategies. You could focus on geological anomalies, places where chemistry or isotope ratios don't quite match expectations. Investigate these anomalies thoroughly, looking for patterns that might indicate artificial rather than natural origins. Most will be natural, but systematic investigation might reveal something unusual. You could examine extinction boundaries in detail. Mass extinctions create distinct layers in rock, marking rapid environmental change. If any extinction was triggered by civilization collapse, that boundary layer might contain elevated concentrations of industrial materials, unusual isotopes, synthetic molecules. Most extinctions are natural, but careful geochemical analysis of boundary layers might reveal subtle signatures we've missed. You could study sediment cores from ancient lakes and ocean basins, looking for chemical anomalies that cluster together in ways suggesting technological activity rather than natural processes. Isolated anomalies could be natural variation, but multiple unusual signals appearing simultaneously might warrant deeper investigation. Ice cores are useful for recent periods. They preserve atmospheric chemistry going back hundreds of thousands of years, but ice doesn't persist for millions of years. The oldest ice cores are about 1 million years old, far too recent to detect ancient civilization in the time frames we're considering. Amber is another preservative medium. Tree resin fossilizes into amber, sometimes preserving organic materials in exquisite detail. If ancient civilization existed in forested regions, their artifacts might occasionally have been encased in resin and preserved. But amber deposits are rare and geographically limited, making systematic searching impractical. There's also the possibility of looking in completely unexpected places. Maybe ancient civilization developed underground for some reason, or in ocean environments, or in regions that are now completely inaccessible. Maybe their technology was so different from ours that the traces they left don't resemble what we expect. Maybe they existed in environments we haven't considered or during time periods we've assumed were impossible for technological development. The fundamental problem is that we're looking for something we might not recognize in places we might not have thought to search, in rock formations that might have been destroyed or transformed beyond recognition. And even if we find anomalies, even if we detect unusual chemistry or strange isotopes or unexpected molecules, proving artificial origin is almost impossible when natural processes can create such diverse phenomena. This is why the Silurian hypothesis is more about epistemology, what we can know, than about archaeology. It's not proposing we go dig up ancient cities. It's asking whether we could detect ancient civilization even if evidence exists. And the answer is uncomfortable. Probably not, unless we get very lucky, and possibly not even then, because our frameworks for interpreting data might blind us to what we're seeing. Where to look, everywhere and nowhere. In the rock we've already examined, reinterpreting anomalies we've explained away, informations we haven't studied carefully because they're difficult to access or didn't seem interesting. In the gaps of the geological record where data is sparse and interpretation is uncertain. In the ambiguous edges of our understanding where natural and artificial might be indistinguishable. But ultimately, the search might be futile, not because evidence doesn't exist, but because time is won. The evidence has been scattered, degraded, transformed, and mixed with natural processes until distinguishing it from background becomes impossible. We're searching for ghosts in a world that erases ghosts, trying to find traces of intelligence in a geological record that reduces everything to chemistry and isotopes and ambiguous signals that could mean anything or nothing. So what if it's true? What if we're not the first technological civilization Earth has produced? What if something rose before us, built cities, developed industry, and then vanished, leaving only ambiguous traces we've been misinterpreting as natural phenomena? The implications are profound and uncomfortable. First, it means we're not special. The assumption that we're unique, that intelligence and technology are singular events in Earth's history, would be wrong. We'd be repeating a pattern, following a path that was walked before, rediscovering what was already discovered millions of years ago. Everything we've achieved, agriculture, writing, science, spaceflight, might be things that happened before, in forms we'll never know, by intelligences we'll never identify. This challenges human exceptionalism at its core. We like to think we're the pinnacle of Earth's evolutionary history, the first time the planet produced something capable of understanding itself. But if we're not first, we're just another iteration, another attempt, another species stumbling along a path that leads where exactly? Because that's the second implication, the darker one. If an ancient civilization existed and then vanished, what destroyed them? Natural disaster? Or did they destroy themselves? And if they destroyed themselves, what does that say about our own trajectory? This connects directly to the Great Filter concept in the search for extraterrestrial intelligence. The Fermi paradox asks, if life is common, where is everyone? Why don't we detect alien civilizations? One answer is the Great Filter, some challenge that prevents civilizations from persisting long enough to become visible across interstellar distances. Maybe the filter is behind us. Getting to our level is incredibly rare, but once you're here, continuation is feasible. Or maybe the filter is ahead. Reaching our level isn't that rare, but persisting beyond it is nearly impossible. Most civilizations destroy themselves through war, environmental collapse, resource depletion, or some other catastrophe that prevents them from achieving long-term stability. If ancient civilization existed on Earth and then vanished, it suggests the filter might be ahead. It suggests technological civilization inherently destabilizes itself, that the same capabilities enabling technology also enable self-destruction, and that surviving long enough to become truly sustainable is extraordinarily difficult. We're currently facing challenges that could become existential: climate change, nuclear weapons, artificial intelligence, biotechnology, environmental degradation. If ancient civilization existed and failed to navigate similar challenges, it suggests these challenges might be fundamental, that every technological civilization faces them, and that most don't survive. That's terrifying. It means our current trajectory might not be unusual or avoidable, but typical and almost inevitable. It means the silence of the cosmos might not be because intelligence is rare, but because intelligence tends to destroy itself before achieving interstellar presence. But there's another, more unsettling implication. If ancient civilization existed and we can't detect it, if the evidence has been so thoroughly erased that we're arguing about whether it's even possible to search for it, what does that say about our own long-term legacy? In 100 million years, if humanity vanishes, what will remain of us? According to the Silurian hypothesis framework, almost nothing. Our cities will be dust. Our plastics will be degraded. Our nuclear isotopes will have decayed. Future geologists might find chemical anomalies, might detect slight isotope excursions, might notice an extinction event in the fossil record. But they probably wouldn't reconstruct our civilization, wouldn't know we built cities and wrote books and contemplated the cosmos. We'd be forgotten. Not just personally, everyone understands individual lives are temporary, but civilizationally. Everything humanity has created, every achievement and discovery and work of art, would be erased from the geological record as thoroughly as if it never happened. Future intelligence, if it emerges, would be as ignorant of us as we are of potential predecessors. This is cosmically humbling. We build monuments hoping they'll last, create art hoping it will endure, make discoveries hoping they'll be remembered. But geological time renders all of this futile. No monument lasts forever. No artwork survives millions of years. No discovery persists when the very rock encoding it gets recycled by plate tectonics. Our legacy isn't secure. It's temporary, provisional, dependent on civilization continuing to preserve it. If we vanish, our legacy vanishes with us. And if we've already been forgotten once, if ancient civilization existed and left no readable legacy, we might be forgotten too. Our entire existence reduced to ambiguous chemical traces that future geologists explain away as volcanic eruptions or natural climate variation. This raises questions about meaning. What's the point of achievement if it's ultimately erasable? What's the value of understanding if that understanding won't persist? Why create if creation is temporary? These are old philosophical questions, but the Silurian hypothesis makes them concrete and geological. It's not abstract pondering about mortality. It's recognition that everything our species creates will be ground to dust by processes we cannot stop, that our mark on Earth is as temporary as footprints on a beach, that we're riding in sand while the tide approaches. But maybe that's exactly the point. Maybe the temporariness is what gives things meaning. Maybe achievement matters not because it lasts forever, but because it exists now, because we experience it, because it shapes the present even if it doesn't survive into deep time. Ancient civilization, if it existed, is gone. Their buildings are dust, their knowledge is lost, their existence is reduced to ambiguous traces we're debating whether we could even recognize. But while they existed, their achievements mattered to them. They lived, created, understood their world, experienced consciousness, and curiosity and wonder. And then they vanished. And now we're here doing the same thing, possibly heading toward the same fate, creating and discovering and achieving, despite knowing it's all temporary, despite knowing that geological time will erase us as thoroughly as it might have erased them. There's something both tragic and beautiful in this. Tragic because nothing lasts, because all achievement is temporary, because we're building on ground that's already forgotten previous builders. Beautiful because we do it anyway, because the ephemeral still matters, because consciousness arising briefly to contemplate the universe is valuable, even if that consciousness doesn't persist. If we're not the first civilization Earth has produced, it means intelligence keeps emerging, keeps building, keeps reaching toward understanding, despite knowing or not knowing that it's temporary. It means the universe, or at least this planet, has a tendency toward consciousness, toward complexity, toward self-awareness arising and asking questions even when those questions lead to unsettling answers. And it means we're part of something larger than individual human existence. We're part of a pattern, possibly repeating, where intelligence emerges, flourishes briefly in geological terms, and then fades, leaving only traces too subtle for the next emergence to recognize clearly. We might be alone in this iteration, or we might be the latest in a series. Either way, we're here now, conscious now, capable now of understanding our place in deep time and contemplating our relationship to this ancient planet that birthed us and might have birthed others before us. The Silurian hypothesis doesn't answer whether ancient civilization existed. It probably can't be answered definitively, but it asks us to consider the possibility, to question assumptions we don't usually examine, to recognize how thoroughly time erases evidence and how limited our knowledge of Earth's deep history actually is. And it asks us to consider our legacy not as something that will last forever, but as something that matters now, that shapes the present, that gives meaning to existence, even knowing that meaning won't persist into geological futures, where our entire civilization might be reduced to a thin layer of strange isotopes that future geologists notice briefly before moving on to more interesting questions. We're temporary. Possibly not first. Probably not last if life persists. Just one emergence of consciousness among possibly many, doing what consciousness does, creating, understanding, asking questions, before time erases the answers and the questions alike. And somehow that's enough. Tonight, place your hand on the ground again. Feel the earth beneath your palm. This planet is ancient beyond your ability to truly comprehend. It has existed through timescales where continents drift, where mountains rise and erode to nothing, where life itself transforms and deforms unrecognizable from what came before. And we've been here, modern humans, with our technology and cities and questions, for barely an instant of that vast history. We assume we're first. It's such a fundamental assumption that we rarely even acknowledge making it. Of course, we're the first technological civilization Earth has produced. Of course, intelligence and industry are singular events in planetary history. Of course, nothing came before us. But what if that assumption is wrong? What if the ground beneath your hand has supported other cities, other civilizations, other intelligences that rose and fell millions of years before the first human existed? What if we're not discovering civilization, but rediscovering it? Not innovating, but reinventing, not breaking new ground, but walking paths that were walked before and then erased by time? We can't know for certain. That's the most honest answer the Silurian hypothesis provides. After enough geological time, after enough erosion and burial and metamorphism and tectonic recycling, evidence becomes too degraded, too ambiguous, too mixed with natural processes to provide certainty. We're left with possibilities rather than proof, with questions rather than answers, with a recognition that our knowledge of Earth's deep history is far more limited than we usually acknowledge. The geological record is fragmentary. Most of it is missing, destroyed by the same processes that created it. What remains is biased, incomplete, heavily edited by time. We're reading a damaged book with most pages torn out, written in a language we only partially understand, describing events so far in the past that even basic geography has changed. And we're trying to reconstruct not just what happened, but who was there, whether intelligence existed, whether technology emerged and vanished. It's possible ancient civilization existed. Possible but unprovable. The evidence, if it exists, is too subtle, too degraded, too easily explained through natural mechanisms. Chemical anomalies could be ancient industry or unusual volcanism. Isotope excursions could be fossil fuel burning or massive carbon releases from natural sources. Extinction events could be civilization collapse or asteroid impacts or climate variation. We have no reliable way to distinguish between these possibilities after millions of years of geological processing. And even if we found something unambiguous, synthetic molecules that couldn't form naturally, isotopes that couldn't exist except through technology, structures that couldn't be explained as geological formations, we'd still face the question of whether we're interpreting correctly. Science is conservative, properly so. Extraordinary claims require extraordinary evidence. An ancient civilization existed is an extraordinary claim that would require evidence so clear, so overwhelming, that ambiguity becomes impossible. We probably don't have that evidence. Probably won't find it. Probably can't find it because time has won, because geological processes have been too thorough, because the Earth recycles its own surface and erases its own history as thoroughly as if that history never happened. So we're left with uncertainty, with the possibility that we're not first, that intelligence has emerged before, that everything we're achieving has been achieved before and then forgotten, and with the recognition that if ancient civilization did exist, we're as ignorant of them as they are now of us, separated not by space but by time, unable to communicate across the vast gulf of millions of years that lie between us. This should be humbling. Not just personally, everyone understands individual mortality, but civilizationally. Everything humanity has built, every discovery and invention and achievement exists in the final eye blink of Earth's history. We've been here barely long enough to matter in geological terms. And if we vanish, if our civilization collapses or evolves into something unrecognizable, or spreads beyond Earth, leaving this planet behind, what will remain of us? According to everything we've explored, almost nothing. Our cities will erode. Our monuments will crumble. Our plastics will degrade. Our isotopes will decay. Future geologists, if they exist, might notice chemical anomalies in rock from our era. They might detect an extinction event if we trigger one. They might find faint traces suggesting rapid industrialization occurred. But they probably won't reconstruct our civilization. Won't know we built pyramids and wrote symphonies and sent probes beyond the solar system. We'll be forgotten. Not just our individual names, those are already lost to most of history, but our collective achievements. Our entire civilization, our existence as a technological species. The geological record will note an extinction, some chemical anomalies, and then move on. Everything we consider important, everything we're creating and preserving and trying to make permanent, will be reduced to ambiguous traces that future scientists explain away as natural phenomena. This is the fate we face if we vanish. The same fate that might have already claimed previous civilizations were completely unaware of. Time erases, geology recycles. The planet continues indifferent to intelligence, unconcerned with legacy, simply operating according to physical processes that grind everything down and create everything new in endless cycles. But here's what makes this tolerable, even meaningful. We're here now, conscious now, capable now of understanding our place in deep time and contemplating our relationship to this ancient planet. Ancient civilization, if it existed, is gone. But while they existed, their achievements mattered to them. They experienced wonder and curiosity and the satisfaction of understanding. They were conscious, briefly, in a universe that's mostly unconscious. They asked questions, even knowing or not knowing that answers wouldn't persist. And now we're doing the same thing. Possibly for the first time, possibly for the 10th time. It doesn't matter ultimately, because the meaning isn't in the legacy. The meaning is in the existence, in the experiencing, in consciousness arising and contemplating and creating despite knowing it's temporary. If we're not first, it tells us something important about this planet, that it tends toward intelligence. That consciousness keeps emerging, keeps building, keeps reaching toward understanding. That intelligence isn't a singular accident, but a pattern, possibly repeating, where awareness arises and asks questions and seeks meaning before fading back into the geological background. This makes us part of something larger than human civilization, part of Earth's tendency toward consciousness, toward complexity, toward self-awareness. Whether we're first or latest or somewhere in between, we're manifestations of something the planet does, produces intelligence, gives rise to creatures that can contemplate existence, enables matter to become aware of itself. And if previous intelligences existed and vanished, it means the planet continues, that life continues, that consciousness continues to emerge even after setbacks and extinctions and collapses. It means we're not the end of the story, even if we're not the beginning. We're a chapter in something ongoing, something that began billions of years ago and will continue long after we're gone, something that tends toward awareness, even knowing awareness doesn't last. This should change how we see ourselves, not as masters of Earth, but as temporary inhabitants, not as the pinnacle of evolution, but as one attempt among possibly many, not as permanent, but as ephemeral, meaningful despite rather than because of our brevity. We matter now. What we create matters now. The understanding we achieve matters now. But it won't matter later, when we're gone, when time has erased us, when future intelligence emerges and contemplates the cosmos without knowing we preceded them. And somehow that's liberating. It frees us from the burden of needing to be permanent, from having to achieve eternal legacy, from requiring that our mark on Earth lasts forever. It doesn't have to last. It just has to exist now, to mean something to us, to shape the present moment in which we actually live. Ancient civilization, if it existed, achieved this. They built, created, understood, experienced consciousness, asked questions, found answers, and then they vanished. And their vanishing doesn't make their existence meaningless. They were here. They mattered to themselves. They experienced what it means to be conscious in a vast, ancient, mostly unconscious universe. Now we're here, doing the same thing, experiencing the same wonder, asking the same questions that might have been asked before and will probably be asked again. Not because we'll last forever, but because consciousness, briefly arising, does these things. It's what awareness does: contemplates, questions, creates, seeks understanding, knowing or not knowing that understanding is temporary. So what does it mean that we might not be first? It means we're part of a pattern. It means Earth generates consciousness repeatedly, that intelligence keeps emerging despite knowing or not knowing it's temporary. It means the universe, or at least this small corner of it, tends toward awareness, toward complexity, toward matter organizing itself into forms capable of understanding. And it means that when you place your hand on the ground, when you feel the ancient earth beneath your palm, you're touching something that's been here far longer than you can comprehend, that might have supported other hands before yours, other consciousnesses contemplating their place in time, other civilizations that rose and fell and were forgotten as thoroughly as if they never existed. You can't know if they were there. Probably weren't. Probably were first, and all the geological anomalies are natural, and the assumption we've always made is correct. But you can't know for certain. And that uncertainty, that possibility, that recognition that we might be repeating rather than inventing, that changes. Something about how you see yourself and your species and your relationship to this planet that's so much older than you are. Look at the rocks beneath your feet. They're ancient, transformed, recycled from materials that might once have been something else entirely. The atoms in your body are older still, forged in stars that died before the solar system formed, scattered and reformed and incorporated into new forms countless times before ending up in you. You're made of stardust, quite literally. And so was any ancient civilization that might have existed. Same atoms, different arrangements, different consciousnesses arising from the same fundamental materials the universe provides. We're temporary arrangements of ancient matter, briefly aware, contemplating our origins and futures, asking questions about whether we're alone in time, whether others came before, whether patterns repeat. And the answer we don't know, probably can't know, might never know, is both unsatisfying and profound. Unsatisfying because certainty is comfortable and uncertainty is not. Profound because it reveals the limits of knowledge, the boundaries of what can be discovered, the recognition that some questions might not have definable answers, no matter how carefully we search. So tonight, knowing what you now know, understanding the possibility that we might not be first, recognizing how thoroughly time erases evidence and how limited our knowledge of deep history actually is, look at the world differently, not with certainty, but with appropriate humility, not claiming to know what can't be known, but acknowledging what's possible. We're here now, conscious now, capable now of contemplating these questions. Whether we're first or 10th, whether others came before, or we're genuinely alone in time, we exist in this moment, aware and curious and seeking understanding. That's what matters. Not because it will last forever, but because it exists now, because consciousness arising briefly to contemplate the cosmos is extraordinary regardless of whether it's happened before. And if ancient civilization existed, If they rose and built and understood, and then vanished, leaving only ambiguous traces, we're still debating. They had this same moment, this same awareness, this same wonder at existence and curiosity about their place in time. And they mattered to themselves in their present, even knowing or not knowing they were temporary, just as we matter, just as any future consciousness will matter. Because mattering isn't about duration. It's about experience, about awareness, about briefly understanding the universe that created you. The earth beneath your hand is ancient. You are temporary. And somewhere between those extremes lies the strange, brief, extraordinary fact of your consciousness contemplating both. That's enough. That has to be enough. Because it's what we have, this moment, this awareness, this capacity to ask questions, knowing some might not have answers. We might not be first. Probably are, possibly aren't. Can't know for certain. And have to live with that uncertainty, that ambiguity, that recognition that our place in Earth's history is less secure than we'd like to believe. But we're here, now, conscious, asking these questions, creating meaning despite temporariness, understanding despite uncertainty, being aware despite knowing awareness won't persist, and that brief flowering of consciousness in an ancient, unconscious universe, that's what makes us matter, whether we're first or last or somewhere in between.